The monster's black hole is at the focal point of the Milky Way. Cosmologists have caught the very first picture of the monster's dark opening at the focal point of our world, giving the primary direct proof of the vast Goliath's presence. Found 26,000 light-years away, Sagittarius A is a gigantic tear in spacetime that is multiple times the mass of our Sun and 40 million miles, 60 million kilometers, across. The picture was caught by the Event Horizon Telescope, EHT, an organization of 8 synchronized radio telescopes set in different areas all over the planet. As not even light can get away from the strong gravitational draw of a black hole, it's difficult to see Sagittarius A itself besides as the outline of a ring of fluffy, distorted light. This corona comes from the superheated, sparkling matter whirling around the entry to the infinite beast's throat at near the speed of light. When the gradually stripped and destroyed plasma plunges over the black hole's incline or occasion skyline, it is lost inside for eternity. Black holes are locales of the room where the gravitational force areas of strength are such an extent that nothing, not even light, can escape. As opposed to space, dark openings are stuffed with the issue that gets fit into a little space. Physicist Carl Schwarzschild inadvertently found black holes in 1916, when he was sorting out a specific answer for Einstein's overall hypothesis of relativity. He was attempting to track down the answer for the gravitational draw of a solitary, single, symmetric bundle of an issue, like the Sun at the focal point of our planetary group. Yet, the arrangement contained an exceptional component. The hypothesis acted unusually at a particular span, referred to at present as the Schwarzschild range. It was subsequently acknowledged why this range was so extraordinary. Assuming you compacted the mass of an particle into a space more modest than that span, its gravitational draw would overpower each known power and nothing could get away. Early physicists accepted that this present circumstance could never be found in nature. Yet, in the last part of the 1930s, nature could for sure permit black holes to exist when Indian physicist Subramanian Chandrasekhar found that over a specific thickness, no power can overpower gravity. Be that as it may, black holes can frame under the most outrageous circumstances. Our outcomes are the most grounded proof to date that a black hole lives at the focal point of our cosmic system. Siri Yunsi, an astrophysicist at University College London and an EHT associate, said in an explanation. The fact that binds the cosmic system makes this black hole the magic. It is critical to how we might interpret how the Milky Way shaped and will advance from now on. Researchers have long imagined that a tremendous supermassive black hole should sneak at the focal point of our universe, its gravity tying the Milky Way's residue, gas, stars and planets in a free circle about it and causing stars close by to quickly circle it. This groundbreaking perception, which shows light being bowed around the space-time traveling behemoth, puts their doubts undeniably. We were dazed by how well the ring size concurred with forecasts from Einstein's hypothesis of general relativity, Jeffrey Bauer, an EHT associate and space expert at Academia Sinica, Taipei, said in an explanation. These phenomenal perceptions have extraordinarily worked on how we might interpret what occurs at the actual focal point of our world and deal new bits of knowledge on how these Goliath black holes cooperate with their environmental factors. Einstein's hypothesis of general relativity depicts how monstrous particles can twist the texture of the universe, called space-time. Gravity, Einstein found, isn't delivered by a concealed power, yet is just our experience of room-time bending and contorting within the side of issue and energy. Black holes are focused in space where this distorting impact turns out to be areas of strength for being the point that Einstein's conditions separate, causing all close-by issues as well as all close-by light to be sucked inside. To fabricate a black hole, you need to begin with an enormous star, one with a mass about 5 to multiple times that of the Sun. As bigger stars approach the closure of their lives, they begin to combine heavier and heavier components, like silicon or magnesium, inside their consuming centers. Be that as it may, when this combination cycle starts framing iron, the star is on its way to a brutal implosion. Iron takes in more energy to intertwine than it gives out, making the star lose its capacity to push out against the huge gravitational powers produced by its colossal mass. It falls in on itself, pressing initially its center, and later all the matter near it, into a mark of minuscule aspects and endless thickness, a peculiarity. The star turns into a black hole, and past a limit called the occasion skyline, nothing, not even light, can get away from its gravitational draw. Precisely how black holes might develop to become supermassive in scale is as yet a secret to researchers, although perceptions of the early universe recommend they could inflatable to their colossal sizes by eating on thick billows of gas and converging with other black holes. The EHD caught the picture, close by the picture of one more supermassive black hole at the focal point of the M87 system, back in 2017. The picture of the M87 dark opening was delivered in 2019. Live Science recently detailed it. However, it required 2 additional long periods of information examination before the Milky Way 1 was prepared. Part of the purpose for the postponement is the tremendously various sizes of the 2 supermassive black holes, which thusly influence the rates at which their plasma mists spin around their focuses. The M87 black hole, M87, is multiple times greater than Sagittarius A, tipping the scales at a stunning 6.5 multiple times the mass of our Sun, and its sweltering plasma requires days or even a long time to circle it. The plasma of Sagittarius A, on the other hand, can whip around it in only minutes. This implies the splendor and example of the gas around SGR-A was changing quickly as the EHD collaboration was noticing it, a piece like attempting to take a reasonable image of a doggy rapidly wasting time. Chi Quan-Chan, an EHD partner and astrophysicist at the University of Arizona, said in an articulation. The imaging system was made significantly more testing by the Earth's area at the edge of the Milky Way, meaning the scientists needed to utilize a supercomputer to sift through impedance from the incalculable stars, gas and residue mists tossed among us and Sagittarius A. The end product is a picture which looks the same as the 2019 depiction of M87, even though the 2 black holes are themselves unfathomably disparate in scale. This is the sort of thing the scientists property to the frightening and persevering precision of Einstein's overall relativity conditions. We have 2 various kinds of cosmic systems and 2 altogether different black hole masses, yet near the edge of these black holes they look incredibly comparative, Sarah Markov, an EHD partner and astrophysicist at the University of Amsterdam in the Netherlands, said in an articulation. This lets us know that overall relativity administers these items very close, and any distinctions we see further away should be because of contrasts in the material that encompasses the black holes. Nitty-gritty examination of the picture has previously empowered researchers to mention a few intriguing observable facts about our black hole's tendency. To begin with, it's messed up, sitting at a 30-degree point to the remainder of the cosmic circle. It additionally seems, by all accounts, to be torpid, making it not at all like other black holes, for example, M87, which suck in consuming hot material from neighboring gas mists or stars before slingshotting it back into space at close light rates. The researchers will circle back to a further investigation of both this picture and the one of M87, close by catching better than ever pictures. More pictures won't simply empower better examinations of the black holes, however, will likewise give further developed detail, permitting researchers to perceive how similar black holes change over the long haul and what happens around their occasion skylines. This couldn't provide us with a superior comprehension of how our universe was shaped, yet in addition help in the quest for hints regarding where Einstein's conditions could give way to unseen physical science. That's it for today's video. If you enjoyed the video, please let us know by hitting the like button. And if you like this type of content, then be sure to subscribe so you never miss an upload. Thank you for watching.